On September 30th, 2017, an Airbus A380 cruising high over the North Atlantic suffered one of the most dramatic engine failures in recent aviation history. Air France Flight 66 was flying from Paris to Los Angeles when a loud bang shook the cabin. One of the 4 engines had torn itself apart. The entire front fan assembly had separated in flight, shredding the nacelle and scattering debris into the sky. The crew diverted to Goose Bay in Canada and landed safely, but the engine was destroyed. The failure was traced to the engine's fan hub, the massive rotating component that carries the fan blades. It was forged from a titanium alloy, Ti-64. Nothing unusual there. This is the kind of high-performance application where titanium alloys excel. But when investigators finally pinpointed the failure mechanism, it wasn't overstress, poor design, or conventional fatigue. It was something far more subtle, a hidden weakness of the material that only appears under specific conditions. And it forced the industry to reconsider how it uses titanium. To understand why, we need to look at what's happening inside titanium alloys, all the way down at the atomic scale. If you zoom all the way into a block of pure titanium, you'll find that, like all metals, its atoms packed together in a very regular, grid-like lattice. The underlying unit of this structure is a repeating hexagonal cell, called the hexagonal close-packed structure, HCP. This is how titanium is structured on the atomic scale at room temperature. Heated up, though, and at 882 degrees Celsius, the atoms suddenly become more stable in a different configuration and undergo a phase transformation, rearranging from hexagonal close-packed to a body-centered cubic structure where the atoms are less tightly packed. The lower temperature HCP structure is called the alpha phase. The higher temperature BCC structure is called the beta phase, and the temperature at which the transformation occurs is called the beta transist temperature. The alpha and beta phases behave quite differently because of their different geometries. The HCP alpha phase has fewer easily activated slip systems, specific planes and directions along which defects in the crystal lattice can easily move. This means the alpha phase tends to be stronger and stiffer, but less ductile than the beta phase. Its closer packed structure also makes it more difficult for atoms to move through the lattice, making the alpha phase more resistant to time-dependent deformation like creep, and better able to maintain its structure at high temperatures. You can't actually get completely pure titanium. Even when highly purified, it always contains trace amounts of impurity elements like oxygen, iron, nitrogen, carbon, and hydrogen. The oxygen atoms in particular have a big impact on the properties of titanium. They sit in the gaps between titanium atoms, distorting the lattice structure and making it harder for defects to move through it, which increases the material's strength. Titanium is said to be commercially pure if made up of less than 1% of these impurities, and there are actually 4 different grades of commercially pure titanium, depending on the level of impurity elements. Grades with higher impurity levels tend to have higher yield strength, but reduced ductility, mainly because they contain more oxygen. Commercially pure grades are highly corrosion resistant and reasonably ductile, but have quite low strength, making them well suited to applications like chemical processing equipment or medical devices, where durability in aggressive environments matters more than mechanical performance. But when high strength is essential, like in fasteners, pressure vessels, or aerospace components, titanium is alloyed with other elements to produce materials with much better mechanical performance. Some alloying elements, including aluminum and oxygen, act as alpha stabilizers. They make the alpha phase stable at higher temperatures. The more alpha stabilizers you add, the higher the temperature needed to transform alpha into beta. The transition is also less abrupt. It now happens over a range of temperatures, where both alpha and beta phases can coexist. Other elements like vanadium and molybdenum act as beta stabilizers, lowering the transformation temperature. Add enough of them, and the beta transist temperature can be lowered to well below room temperature. This leads to 3 main categories of titanium alloys: alpha, beta, and alpha-beta alloys, depending on which phases are present at room temperature. Alpha-beta alloys offer a good balance of properties, combining the strength and creep resistance of the alpha phase with the ductility of the beta phase. It's no surprise then that the most widely used titanium alloy falls into this category. Ti-64 contains 6% aluminum, an alpha stabilizer, and 4% vanadium, a beta stabilizer. It accounts for more than half of all commercially used titanium, and is often used in demanding applications, including the fan hub that failed on Air France Flight 66. One of the huge advantages of alpha-beta alloys like Ti-64 is that they can be heat-treated, meaning we can use carefully controlled heating and cooling to manipulate the balance and arrangement of the two phases. In fact, titanium alloys are highly sensitive to how they've been processed, which opens up a wide range of possible microstructures and corresponding material properties. The three variables that matter most are the temperature the alloy is heated to, the soaking time, which is how long the alloy is held at temperature, and the cooling rate. If the alloy is heated above the transist temperature, a process called beta annealing, any existing alpha-beta microstructure dissolves to a uniform beta phase. When subsequently cooled, plates of alpha form inside the prior beta grains, separated by thin films of retained beta. This is called a lamellar microstructure. If cooled faster, the alpha plates form more densely and with a greater range of orientations within each prior beta grain. This creates a distinctive basket weave microstructure, where the plates intersect in a crisscrossing pattern. If the alloy is heated to below the transist temperature instead of above it, both the alpha and beta phases are present before cooling begins. The existing alpha grains remain stable, while the beta phase transforms during cooling into fine plates of alpha, called secondary alpha, separated by thin films of retained beta. The result is called an equiaxed microstructure. It has roughly spherical primary alpha grains distributed within regions of transformed beta. This is called the mill-annealed condition. It's the state Ti-64 is typically supplied in from the mill, and the most common microstructure of in-service Ti-64 components. By heating to just below the transist temperature, you can retain some equiaxed alpha while still forming lamellar regions during cooling. The result is a bimodal microstructure that has a deliberate mix of equiaxed grains and lamellar plates. If cooling from above the transist temperature is done very rapidly, by quenching in water for example, the beta phase transforms almost instantaneously into a very fine, needle-like structure called alpha prime. Alpha prime has the same underlying hexagonal close-packed structure as normal alpha, but because cooling is too fast for the atoms to fully rearrange, the lattice is trapped in a strained, distorted configuration. This is called martensite. The alloy can then be reheated to around 500 degrees Celsius in a process called aging. This causes the strained alpha prime phase to break down into a fine mix of alpha and beta. The very fine scale of the resulting microstructure creates numerous phase boundaries that hugely impede the motion of dislocations through the lattice, which significantly increases strength. Each of these microstructures, lamellar, basket weave, equiaxed, bimodal, and martensite, can be either fine or coarse, depending mainly on how long the alloy is held at high temperature. This makes titanium alloys very versatile. With the same chemical composition, you can produce a huge range of different microstructures just by changing the thermal processing route. These different microstructures lead to different material properties. An equiaxed structure might be chosen for conventional fatigue resistance, a lamellar or basket weave structure for fracture toughness or high temperature performance, and a martensitic structure for high strength. Titanium alloys, including Ti-64, are mainly used in high-performance applications, where their high cost can be justified by three key advantages: good performance at high temperatures, outstanding corrosion resistance, and an unmatched strength-to-weight ratio. When SpaceX engineers were first designing the Falcon 9 rocket, a key challenge was figuring out how to guide the booster back down to Earth. They decided to use grid fins, small gridded control surfaces that help steer the booster during descent and landing. At first, these were made from an aluminum alloy, but engineers soon realized the material wasn't quite up to the job. Although it was very light, it only barely withstood the intense aerodynamic heating experienced during descent. They eventually made a change, swapping out aluminum for a titanium alloy that could survive the extreme heat over and over again, unlocking true reusability. Titanium's corrosion resistance is just as impressive. To understand why, we need to look closely at what happens at the surface of the material. The moment a fresh titanium surface is exposed to air, oxygen atoms react instantly on contact with the surface, forming an extremely thin layer of a tightly bonded material called titanium dioxide. This layer grows as oxygen migrates inwards, until it reaches a thickness of around 5 nanometers. At which point, the oxygen can no longer move through it, and the layer is fully established. Despite being so thin, this layer passivates the titanium, acting as a very effective barrier that prevents the atoms underneath it from reacting with the environment. This allows titanium to resist attack in a wide range of environments with very little degradation compared to most structural metals. This is even true inside the body. The corrosion resistance and chemical stability provided by the oxide layer give titanium exceptional biocompatibility, making it an excellent material for medical applications, like dental implants, hip replacements, and bone plates. Even more remarkably, bone can actually bond directly to and grow on the titanium oxide layer in a process called osseointegration. This creates a strong, lasting connection between the bone and the implant that can actually get stronger over time as the bone remodels and densifies in response to mechanical stress. While the naturally formed oxide layer already provides excellent corrosion resistance, it's sometimes beneficial to increase the thickness of the layer in a controlled way, to increase wear resistance in high contact areas, for example, or to provide electrical insulation, since the passive layer is non-conductive. This is done using a process called anodization. The titanium part is placed in an electrolytic bath, a solution that contains a dissolved electrolyte, allowing it to conduct electricity. The part is connected to the positive terminal of a power supply, making it the anode. A separate part, usually a piece of stainless steel, is connected to the negative terminal and used as a cathode, completing the circuit. When a voltage is applied, the electric field drives oxygen from the electrolyte through the existing oxide layer, where it reacts with the titanium underneath. This can push the titanium oxide layer well beyond its naturally self-limiting thickness of 5 nanometers. The thickness can be precisely controlled by adjusting the applied voltage, allowing it to reach over 200 nanometers. This brings the thickness of the oxide layer closer to the wavelength of visible light, causing it to interact with light waves in interesting ways. When light reaches the titanium surface, some of it reflects immediately, and some enters the oxide layer, reflecting off the underlying titanium instead. The extra distance traveled by the light that passes through the oxide layer causes a phase shift between the two sets of reflected waves. When they recombine, they interfere with each other. Wavelengths that are in phase reinforce one another, and wavelengths that are out of phase cancel out. This effect, called thin film interference, gives the anodized part color. It's the exact same effect you see in soap bubbles or on the surface of an oil slick. The specific color of the titanium part depends directly on the oxide layer thickness, which is controlled by the applied voltage. So anodization isn't just used for protection. It's also a practical way to add those characteristic vibrant colors to titanium parts without any dyes or paints. Corrosion resistance and high temperature performance make titanium valuable in a lot of different applications, but the real reason it's become such an important material in aerospace is another of its defining properties: its incredible strength-to-weight ratio. Titanium has a density that's roughly halfway between steel and aluminum. If a titanium bar has a mass of 100 grams, a steel bar of the same volume would weigh 175 grams, while an aluminum bar would weigh just 60 grams. Stiffness follows the same trend. The Young's modulus of titanium sits between the two other materials, so for the same applied force, the aluminum bar would stretch more and the steel bar would stretch less. It's when we look at strength that titanium starts to get really interesting though. A common aerospace alloy like Ti-6-4 has a yield strength of around 900 megapascals in typical heat-treated conditions. That's much higher than high-strength aluminum alloys and comparable to many structural steels, at less than 60% of the mass. On a strength-to-weight basis, titanium alloys outperform pretty much all traditional structural metals. That's why they're used extensively in aircraft landing gear, where you need high strength but can't accept the mass penalty of steel or the thicker cross-sections you would need with aluminum. In fact, titanium accounts for around 15% of the mass of modern commercial aircraft. You'll find it in the engines too, in compressor blades and discs, shafts, frames, and, of course, in the fan blades and hubs. So what happened to Air France Flight 66? In the months after the incident, search teams began recovering debris from the ice sheet in Greenland. This was a huge operation. Some of the most critical fragments were buried deep in the snow, but were eventually found after almost 2 years of searching thanks to experimental radar technology. This meant the French crash investigators could finally pinpoint the cause, and the results were surprising. They attributed the failure to a crack that initiated early in the life of the titanium fan hub and grew progressively until catastrophic failure. But this wasn't a conventional fatigue crack. The fan hub had failed just a quarter of the way into its expected life, based on normal fatigue assumptions. The real cause was a hidden weakness in titanium alloys, their susceptibility to a unique failure mechanism called cold dwell fatigue. Unlike conventional fatigue, which occurs when a component is subjected to cyclic loading, allowing cracks to grow incrementally with each stress reversal, cold dwell fatigue occurs when cyclic loading includes a sustained hold at high stress. This kind of loading is common in rotating components in jet engines, which see high-stress dwell periods at various points throughout the flight cycle, including during takeoff and climb, where engine thrust is high and components experience high sustained centrifugal forces. It's called cold dwell fatigue because it occurs at temperatures well below those where you'd normally expect creep or other time-dependent deformation, and in some cases, it can even occur at room temperature. Cold dwell fatigue is a consequence of the alpha phase within the alloy. The hexagonal close-packed structure is highly anisotropic. Its resistance to deformation depends on the direction of loading. The material is much stiffer when a load is applied perpendicular to the hexagonal plane than when the load is applied parallel to it. In the equiaxed microstructure of alpha-beta alloys like Ti-6-4, the hexagonal close-packed structure has a consistent orientation within each alpha grain. Depending on the direction of the applied load, some grains are oriented such that they deform more easily. These are soft grains. Others have an orientation that better resists deformation. These are hard grains. The softer regions deform more than the hard ones when a load is applied, and they keep deforming over time when the load is held, causing the load to redistribute and gradually shift onto the harder regions. This isn't a problem when orientations are random from grain to grain. The redistribution happens everywhere, so no single region accumulates too much stress. But the danger arises when the material contains a large cluster of similarly oriented grains, forming a so-called microtexture region, or macro zone. These regions can form when groups of alpha grains inherit similar orientations from the larger prior beta grains they formed within, and deformation applied during forging isn't sufficient to fully break up and randomize these orientations. A cluster of grains that's hard relative to the load direction doesn't contain any soft grains within it to redistribute the applied stress. Under prolonged dwell loading, the softer surrounding material continues to deform, transferring more and more load into the hard region, and creating a stress concentration that can cause cracking to initiate. And that's exactly what caused the engine failure on Air France Flight 66. The French investigators concluded that dwell periods accelerated the initiation of a crack in a microtexture region in the fan hub, which cyclic loading then grew to failure. Cold dwell fatigue failures had happened before, but it was thought to mainly affect alpha alloys. This was the first time a component made of Ti-64, the workhorse titanium alloy of the aerospace industry, had failed in service due to cold dwell fatigue. This had huge implications. Two parts could have identical compositions, identical strength and ductility, pass every standard qualification test, and yet have hugely different dwell fatigue lives depending on their grain structure. The industry responded immediately. Fabrication methods were re-examined to minimize microtexture regions. New techniques were developed to map grain orientations in forging samples, and inspection regimes were tightened to check for early cracking in the existing fleet. Titanium is an extraordinary material, and millions of titanium components fly safely every day. But the failure of Air France Flight 66 showed that even the most well-understood materials can behave in unexpected ways, and sometimes it takes a failure to push our understanding forward. Whether you're designing titanium aerospace components, developing mechanical systems, or just 3D printing parts at home, having the right tools makes a huge difference to how quickly ideas can turn into working designs. And that's why I'd like to introduce you to this video's sponsor, Onshape. Onshape is a professional-grade CAD platform that takes a new approach to CAD, solving many of the frustrating limitations of traditional design tools. For one thing, it's completely cloud-based. There's no software to install. Your designs live online, and you work on them directly in your browser. The heavy computation happens remotely, so you don't need a powerful workstation to handle complex models, and you can access your work from anywhere, even on the go using the mobile app. This makes collaboration really easy. If you want feedback from a colleague or a supplier, you just share a link to the model that they can open directly in their browser, where they can leave comments right on the geometry. Everyone's always working from the same version, so you don't end up with multiple files floating around, with no idea which is the latest. One of my favorite features is the powerful GitHub-style versioning system. If someone wants to try a new idea, they can create a branch and work on it without disrupting the main design, then merge it back in later if it works. There are loads of other thoughtful design features built into the platform, like make connectors, defined connection points that let you position parts with a single constraint, making assemblies much easier to build, or feature script, a programming language built into Onshape that allows the platform to be extended with custom modeling tools that can be shared within the community. All these features create a rich design environment where it's easy to iterate, collaborate, and move projects forward, which all leads to more efficient engineering. For commercial teams, the professional plan adds even more capabilities, including built-in simulation tools, PCB design, and CAM toolpath generation. It even supports model-based definition, letting you embed important manufacturing information like dimensions, tolerances, and datums directly into the 3D model. Onshape really does feel like the future of engineering design, and you can use it for free. Head over to onshape.pro/efficientengineer to get started. And if you're interested in the advanced capabilities of Onshape Professional, you can use the link to get a 6-month free trial. And that's it for this look at titanium and its alloys. Thanks for watching.